the video being posted. Like the view count is going to be like 2, and it's going to be you. This is just for our internal purposes. And if you want me to make it by default not visible, then we can do that too. Just let me know. Okay, so we're going to talk through some of the basics of numerical methods. I'm going to give this, let's see, view as slideshow. We'll see if this is nice. This is really the first time I'm doing it this way. So essentially what we're trying to do here is to go from thinking about like purely theoretical models to think about numbers with our models. The nice thing, Hu and I were talking about theoretical models in the hallway during our break. The nice thing about theoretical models is we can leave them very general, right? So you've seen in your higher level theory classes, just generic, systems of equations where we don't actually use numbers, we use variable names. Like your Greek alphabet soup that you've seen in intermediate. This is really nice in a lot of ways, but sometimes we actually want to be a little more detailed and sort of go from something abstract to something more concrete. We lose some of the abstraction, but we gain some specificity. In general, like the way I start thinking about models, especially when I'm trying to estimate them, I start theoretical, right? Like I'm going to set up the theoretical set of equations, the model that I'm interested in, and then I'm going to take that and then try to become more specific from it. The theory is how you structure your thought to think about the different variables and such, and then defining like the inputs and outputs and all of that, and the objective function, which we've talked a little about the capstone project and how you might do that. But generally, like these things can be, they're a great place to start, but often solving them is really challenging. And sometimes it's not even worth attempting to solve. Can be complicated, and we also want to generally move from a model to data to make things concrete, right? Like sometimes there are purely theoretical results that matter, like comparative statics. Sometimes they come out to be really clear predictions, but sometimes the result depends on the values of the parameters themselves. And so often we care about the parameters, not just the theoretical. So what we're going to do is, in numerical methods, we're going to start this today, and then we're going to continue it on Thursday. We're going to try to mirror the analytical skills from theory, but we're going to do this with a computer. So we're going to solve systems of equations. When we have specific parameter values, we're going to work through how we do that with a computer. And then we'll also think about how we how we actually go about estimating the parameter values later in the semester. Okay, so here's the basic setup here. There are 3 main parts of what we're doing. So we're going to think about numerical derivatives, so how we can use a computer to give us derivatives to things that are just very challenging to do. I'm going to show you 3 examples getting increasingly challenging. And then we'll think about numerical solutions to equations, so how we have a system of equations, and then we can use a computer to actually go about solving that. And then next time we'll talk about numerical optimization. So this is, we have a system of equations. How do we go about maximizing a thing? Okay, so this is just some imports. I'm going to run this. I have some colors here we'll use throughout. These are just, PIT standard colors. I got them from this link. You can take a look at that. All right, so this is just, like this is a thing you've seen so many times before. We have two x variables. You could think of this as x and y, just a standard system of equations. You might be able to do this in your head, right? Like the way you solve this, giving me the side eye. Maybe you can't do this in your head. It's been a while since I've thought about these things from linear algebra. But the way you can do this, right, is multiply this bottom row by 2. So it's 2x1 plus 2x2 is equal to 4. And then you just subtract the second one from the first one, which gives you the 2x1, subtract from 2x1, 0x1. So all we're left with is 3x2 minus 2x2, which is 1x2. And then we have 6 minus 4 is 2. So x2 is equal to 2. And then we can plug that into the second equation to show us that x1 is 0. So the unique solution here is x1 is 0 and x2 is 2. If you can't do this in your head, you're in great company. This is the solution. This is maybe a little bit dramatic to say it this way, but this is a unique solution. So we can represent these kinds of linear equations as matrix form. Do you all feel familiar with matrix form? Somewhat. Did Andy do any of this?
We did at the very beginning of the year in like our 2-week crash course introduction. I forget what they called it.
Okay.
Base camp.
Base camp, okay. At the beginning of the school year?
Yeah, back in August.
Yeah, okay. So yeah, so this is just another way of representing the same math problem, really. We can represent the coefficients in this first matrix. We're not going to spend a ton of time with linear algebra like this, but this is, I think, a helpful way of thinking about these kinds of problems. This one isn't, like, it's so simple, it's not particularly useful, but it's, I think, instructive. We have our coefficient matrix, and then we have the variables. So this is the data, and then this is the two variables, and then this is the outcome. The standard way we set this up with notation looks like this. So this is A is our big data matrix. So this is a 2 by 2. We multiply that by a 2 by 1 in X, which gives us our 2 by 1 of the outcome C. So that's just a way of setting it up in linear algebra. We can do linear algebra in code. So we're just going to walk through a little setup here with linear algebra in code. So I'm just defining the two matrices, right? So we have A, we have X, and we have C. And we have two things we know. We know A, which is our data matrix, and then we have C, which is our outcome. So I have A, I'm just defining this as an array. And we have the first row is 2 by 3. 2 and 3, so this is 2 and 3 on the top. And then we have 1 and 1 as the second entry. So the way we write this out is we have big brackets, the square brackets, and then inside the square brackets, we have square brackets for the specific rows. So the first one and then the second one. So just this notation here. If you wanted to sort of write this out maybe a little more clearly, you could write it like this. So we have the array just tells Python that it's an array on the outside. We have the square brackets on the outside, which tells it that this is a structured data structure. And then we have our two rows on the inside. Does this feel familiar? You've probably maybe done some of this. This is just like syntax for showing the computer what we're trying to do with math. Okay. So if we wanted to run this again, we could. And then for our C array, we just have the one column. So we don't put the brackets on the outside. This is just the column. So the outer brackets tell us the columns, and then the inner brackets tell us the rows. So we run this, and we get the C and the A. What we can do is actually just go ahead and solve for x. So Python, like every language really, has a linear algebra solver. So this is NP, which is just the numbers package, what we call NumPy. And then we have linear algebra, so linear dot solve. So we're going to put in the A as the first entry. So this is the thing we're multiplying by x. And then we have our C, which is our the thing we're setting it equal to. And then this is going to solve for the x. This is just the standard structure for how we do these things. And then when we run this and we print out the x, the outcome of this, we get 0 and 2, which conforms to the actual analytical solution we found earlier. Okay, so what have we done? We've set up a very simple problem we all probably feel familiar solving. Whether you can do it in your head or not, you could have solved this. And we just did it with a computer. And the way we did this is by representing the system of equations in matrix form and then giving it to a computer to solve using our linear algebra solver. Underappreciated that we can do this with computers. Like your grandparents didn't have this. The fastest thing, the fastest thing at the time was to do this by hand. This is not that useful for this exact solution. Like writing out the code and then putting it into Jupyter and then solving it probably took longer than it would have taken to solve it by hand. But this is the kind of thing we can do with computers that becomes really useful later. You can also do this kind of solution using matrix multiplication. So what we could do is invert the matrix. If we pre-multiply both sides by A inverse, if you remember from your linear algebra, A inverse times A is the identity matrix, which disappears. But we would have X is equal to A inverse times C. So one way of solving this is to get the A inverse, where we put in, we just use the numbers package A inverse, or linear algebra inverse package to invert A. And then we pre-multiply A inverse by C. We have a matrix multiplication operator, this ampersand. That's the at symbol. Ampersand is different. This is the and, yeah. No lecture points, because you were correct. Okay, so yes, there is a name for this, and I'm forgetting it. But this is our matrix multiplication operator. So it allows us to multiply two matrices together. And this, if we run this, this will also give us the same numbers. This is nice in a lot of ways. Depending on your application, you may want to use one or the other. The reason, sometimes the matrix multiplication approach can be unstable. So this is, I think, generally the better approach. But this one might be simpler. Okay, any questions here? Okay, so are you starting to see some of the things we can do here? Computers let us solve trickier problems. Even though this is not a tricky problem, these are the kinds of things we can leverage with computers. You don't have to do all this by hand. Okay, so that was nice for a simple example. And you've seen some of this. You saw this last semester, correct? Like last semester you took like an econometrics sequence. in the fall, like the standard econometrics with like these kinds of things where you're minimizing sum of squared errors and such. This is the standard regression model. So we have our predictor variables, and then this is x is our inputs, and then we have y, which is our outcome variable. So we have this model on the one side, and we're subtracting it off from our outcome variable, and then we're just squaring that error. So the difference between the model and the prediction, or the prediction and the outcome, and we're squaring each one of those differences, and then we're summing them up. The objective of OLS is to minimize this thing. This is a system of equations, as you saw, and you can represent this in matrix form. And all you were trying to do is essentially choose betas to minimize this thing, which is just a linear algebra problem. As you would go through this, you could set it up in this general way as a linear algebra problem. We're not going to spend a ton of time with this. You've seen this before, but this is a way of representing the data, the optimization problem with both x and y. So it looks like this standard system of equations. Whenever we have these kinds of problems, we can set them up as systems of equations. The specific solution to OLS, as you probably remember, looks like this. So our coefficients, our beta hats, are this thing. So it's just this product of the data and the predictor variables and the outcome variable. The dependent variable and the independent variable. And it looks like this, just a product of a bunch of matrices. So this is how we actually do it behind the scenes. Whenever you run OLS, it's actually doing matrix multiplication. So what's the point here? Just a bit of linear algebra review, showing you that we can solve systems of equations so long as we have the things we're handling. And then giving you an example of how we actually use this. So this is minimizing this sum of squared errors, which gives us a nice formula to work with. Okay, any questions here? The big point, this is all mechanical. We can have a computer do it for us in this particular way. So we've done simple systems of equations. Let's come back to working with functions and using a computer to give us derivatives. So we're going to come back to numerical derivatives. This is, we can calculate derivatives of lots and lots of different things. If you're good with calculus, I think 2 of these will be easy and 1 of them will be hard. I'm going to give you 3 examples. This one, so we have f of x, ax squared plus bx plus c. This is just the power rule. So the derivative of f of x looks like this. So just we have 2ax coming from the power rule of ax squared, plus the second one is just b coming from the power rule, and then the third one, c, no x, so it just drops out. Okay, so this is easy. Let's look at a harder one. This is, if we multiply that original function by e to the negative lambda x, we can also solve this one. This one's maybe a little trickier. Anyone know how we do this? Like what's maybe not the solution necessarily, but the process?
Product rule.
So product rule, yeah.
So you have like f, you could define the function in the parentheses as your f of x.
Yeah.
And then e to the minus lambda x is g of x, and
Yeah.
you have f of x times g prime of x plus g of x times f prime of x.
Yeah, nice. So we have two things multiplied by each other, and then we can just use the product rule. To give us, without like going through the whole process, we could write it out like this. So this one is, also not that challenging, but it would require some thinking, right? It's not quite as simple as the first one. We have the g of x, the derivative of g of x times f of x plus g of x times the derivative of f of x, just the standard product rule. What about this one? So this is square root of x squared times e to the sine of x plus, what's this, sigma, capital sigma, and then we have, which is the normal CDF, which is a really gross function in itself, and then we multiply that by this thing. Can you do this in your head? Can I show you the answer? Yeah. So this one is a lot more challenging, and I wanted to show this to you. These are things we can care about, right? Like, there may be a specific situation where this is the problem you're working with. You want to take a derivative of this crazy looking thing. I mean, it doesn't look so crazy. The derivative just turns out to be complicated. And we may care about the derivative. In this case, you could solve it, right? Like, I have the solution on screen. But the problem, the thing in general, though, is you can care about the solution, but often we don't care about the actual functional form in every case, and sometimes it just takes so long. What we truly want is just a way of approximating this thing. We want to get very, very close without necessarily needing to know what this functional form looks like. So what we're going to talk about is ways of letting a computer approximate these things. So how do we go about computing gradients and derivatives with a computer? Well, let's think about the thing we try to do with derivatives, like going back to your Calc 1 days. A derivative is really just thinking about very small changes. So, we're going from x to x plus some very minuscule movement in the x direction. So these are very small but discrete changes. So it's very small, but it is actually a delta. And then all we're trying to do is calculate this ratio. So how does the function move divided by how the x variable is moving? So this is just like the precursor to the definition of a derivative, right? We're looking at the function evaluated at x plus some very small increment, delta x, and then we subtract off the original, which just tells us how the function is moving when we move x by a little amount. And then we just divide this by the difference between x and x plus delta, which is just delta x. So this is the definition. This is how we define a derivative. The derivative is just, you remember this from your intro class, your Calc 1 class, right? Like, we just take the limit of delta x so that it gets very, very small. And we call this the derivative. So it's just the limit as delta x goes to 0. So this bottom piece goes to 0 weirdly, but when we evaluate these two values, for a well-defined derivative, there'll be a cancellation, and we get the slope at this value of x. Okay, so this is how I want you to think about what we're about to do in the context of the definition of a derivative. A computer can't take this limit, but what a computer can do is approximated. So instead of taking this exact limit, what we're going to do is actually approximate the derivative using two numbers that are very, very close to each other. So instead of actually sending them out with a limit to 0, we're going to actually just use a very, very small value of delta x. So almost like the pre-limit definition. So we're going to do essentially this, but with a very, very small value of x. Okay, so it has to be very small. So delta x, we're going to call this epsilon, but we can't make it too small. Computers aren't infinitely capable. So we want to make it very small, but if we make it like incredibly close to 0, computers will actually run into some problems. So there's a bit of some nuance there. But we can write out a function that actually does a generic derivative for us in this way. How many of you have you worked with function definitions in Python before? No, I'll take that as a no. So let me talk this through. So this first part, this is just the comment. And we can actually get rid of this. I don't particularly care about the comment. All we're doing is trying to define a numerical derivative. This is def, so this is just defining a derivative. So from here on out, after we run this cell, because we're defining num deriv to be this thing, num deriv will be a specific thing that we've defined it to be. We have parentheses, and inside the parentheses, we have arguments. So this is exactly how you define a function in math, right? We write an f of something, and we can have more than one input, and then the function does something or other. Here I have f, so f is the first input. This is just the function that we're going to use. So we submit into the derivative function a function itself. And this is really actually how mathematicians think about the derivative as a function in itself. It's an operator, I should say. And then we're going to define x to be the thing, it's like the variable name that we're taking the derivative with respect to. And then eps is just epsilon. We're going to define how small the increment is. Okay, and then inside I've given it a description. So this is just the forward difference. So we're looking at the forward difference version of the derivative, and we're approximating a numerical derivative. And then this last line here is return. So this is just, we want the function to give us something back. So I'm just defining what that thing is. And what I've written in after the return should look identical to the small difference version of the approximate derivative, right? We have the function evaluated at x plus some small increment, and then we're subtracting off the original x, so the x without the increment, and then we're dividing by the increment. So we have the difference between the two evaluated parts of x, and then we're dividing by the difference. So this should look identical to this thing. So we have the difference on the top, so f of x plus the increment minus f of x divided by the increment itself. So we just written this in some nice little code. Any questions here? The power of code. So we're going to estimate some derivatives. So I'm going to run this, which executes it, which means we've now stored this definition as a derivative. Okay, so that's the derivative version in code. We already know the solution, though. So going back to our easy example, this is the one we know the solution to. If I plug in these actual values directly, so A, B, and C, this thing becomes this. So we have 2x squared minus 10x plus 3. Later in the semester, we'll talk about what if we want to not just take these parameter values as given, but actually estimate them. We can do this with data, like from the real world. If this is like a demand equation, we can just do this directly using data. But here we're just going to take these values as given. This is the derivative that we calculated analytically, right? Just using the power rule. So we have the function itself, which we're going to evaluate using our derivative function, our numerical derivative function. And then we can also just check whether what we're doing is correct using the thing we know. So we're going to check whether we're close between the two. So here, just like I did with the derivative function, any questions here? So just like I did with the derivative function, I'm just going to define, we'll call this easy f. So this is, f of x is equal to 2x squared minus 10x plus 3. So all I'm doing is just defining a function that corresponds to our easy function. So this is 2, and then this is Python for multiply, 2 times x. And then we have star star, which gives us the exponent. So this is star star 2. So 2x squared minus 10 times x plus 3. And then, so this is the function itself, and then this is the derivative of the function, so this is f prime. So we'll put a d in front, so the derivative of easy f, it's 4x minus 10. So if we run this, we can actually just check a few things. So let's say we have easy f. So if we plug in 10, we can calculate what that actual value is. So you can check this if you like, but I trust Python, assuming what we've written is correct. And then we can also plug in the derivative of easy f evaluated at the value x equals 10. And that has a pretty steep slope of 30. Okay, any questions here? Nice. So this is our the way we would set up mathematical operations in Python. What I'm going to do here is run two things. So first, I'm going to define the actual increment, right? To compute a numerical derivative, we need to know what the difference is, the epsilon, the value of the increment. This is scientific notation for it's 0.12345 I think it's 7 zeros. So this is scientific notation for this. So 1 after 7 zeros. So it's a very, very small number. So that's our epsilon. So this is large enough that a computer can handle it. This seems like an incredibly small number. In practice, this is never going to be meaningful. So the difference is never going to be meaningful. You can go smaller, but then you start running into problems. Sometimes this is already too small, so you're going to have to play with that. And then we have our numerical derivative function. So if you remember back, we're going to input into the numerical derivative function the mathematical function that we had just described. So here we have easy f, and then we're going to specify the value of x. So we want to take a derivative of easy f with respect to x at a specific value of x equals 3. So we want the slope at x equals 3. And then we're going to tell it the increment. So how precise do we need it to be? We're also going to evaluate the analytical derivative at 3, and then we're going to compare these two values. And then the last thing I'll do is just show you the error, like the mismatch between the analytical derivative and the numerical derivative that we calculated. What do you all expect? Do you think this will be close? Take that as a yes. So let's run this. This is the analytical derivative. This is the thing we calculated. So the slope of the function f evaluated at 3 is exactly 2. But then our numerical derivative is this value, which you'll notice a few things. First off, it's not exactly 2. This is an approximation. So it's not exactly 2. Because we're not evaluating it exactly at that particular value, we have an epsilon that's not exactly 0. These two things are not identical. But the error is very, very small. And what you can see here is the error has the same sort of order of magnitude as the epsilon. So this won't always be this close, but you can see the order of magnitude is very similar. So this number is like 2 with 7 zeros before it. Okay, any questions here? So what's nice, even though this is a very simple function, these are the kinds of things we can do with numerical derivatives. We don't always care particularly about the functional form of the derivative. Sometimes all we care about is the actual value of the derivative at a particular point. And we can actually take this further. We'll talk about how we can evaluate not just at 3, but we can have a computer actually evaluate the derivative at many, many different points. So this is maybe a slightly harder problem. We talked through how we would actually go about finding the derivative using the product rule. And this is just me coding up that function. So this is, we'll call this medium f, so medium difficulty. You'll remember this is f of x is equal to, this is our original f, so this is 2x squared times 10x plus 3, sorry, minus 10x plus 3. And then I've defined lambda to be 10, or 1 over 10. So we're just going to use this thing. And this is nice. So this is just essentially easy f times, this is just notation for raising something to the e to the something. So this is, negative x over 10 in the numerator. Okay, so nice. And then we actually did go about calculating the analytical derivative. So if I run this, we're going to perform the same operation, but for this slightly harder one. Okay, so if I run this, I get the analytical derivative of medium f evaluated at 3, which is this thing. And then we get the numerical derivative evaluated at 3, which is this thing. And again, just incredibly close. The error isn't quite as good. Well, I guess it's still on the order of magnitude as the epsilon, which is sort of a general rule. It's going to be in the ballpark. Like the order of magnitude of your epsilon it's not always true, but it's going to be pretty close to the order of magnitude of the ballpark of the order of magnitude for the error, the difference between the numerical derivative and the analytical derivative. Any questions here? No questions? So one thing we can do is actually plot these functions. So this is just, you can run this. This is just a figure showing showing medium f. And I'm using our university colors. So the way I draw this figure Do you like talking through the specifics of the code? Some of these things matter a little bit. In general, like these are like the exact implementations of plotting functions is not something I care that you know so much about. I don't think it helps you think through these problems necessarily. But actually what the computer is doing is taking a bunch of values. So lin space is just giving us a bunch of, it's giving us 200 points between 0 and 100. And then all we're doing is evaluating medium f at each one of those little points, those 200 points, and then we're plotting each one of those points. So this is x on the horizontal, and then we evaluate medium f at x at each one of these points. And that gives us this figure. So this is, it's a weird function. This is the medium f, right? So it's, we have that exponent. It looks like this. So what we're doing by evaluating at 3 is evaluating somewhere down here. So we can evaluate at a particular value of x, but we can also evaluate at a bunch of values of x. And we can do that by running through a bunch of values of x and computing the derivative and then plotting the actual value of those points. So what I've done here, let me just talk through the particulars. So this is the derivative of our medium f. And again, I've plotted a range. So this is 0 through 101. So 0 through 101. And we're just going to evaluate the numerical derivative of the medium f function. And all we're doing, this is just a for loop. So we have this little thing. Can I get a temperature check? Do these for loops look familiar? Hands up if they look familiar. Hands up if they look like familiar but a little intimidating. And hands up if they don't look familiar at all. Okay, I love this. I love that you're good with this stuff. It makes my job more fun. So this is just, we're going through, and this is our numerical derivative function that we had set up at the very beginning, right? This is the function we defined. I'm giving it medium f, which is our medium function that we had defined earlier. I'm giving it xi, so this is just different values of x on the horizontal axis. And then this is our epsilon. And I'm just saying, I want to evaluate, I'm going to create a list of numerical derivatives at a bunch of the horizontal axis values. So all of the different places in x range, going from 0 to 101, or to 100. This stops at 100 before we hit 101. So we're just estimating the derivative at each one of the integers from 0 to 100, and we have a big list of them. And then all I'm going to do is plot this. So I have, first off, I have the analytical derivative. So I'm going to plot across this domain, I'm going to plot exactly what the analytical derivative looks like in blue. And then I'm just going to plot, using a scatter plot, each of the numerical derivatives that I've estimated. So we've just gone through and looked at the original medium f function and evaluated numerically the derivative at each one of these points. And then I'm just plotting them x and y as scatter plot. And what you can see, I have the original functional form in blue, and then I have the numerical derivatives estimated at each one of these points in yellow. Two great looking colors. They go very well together. And what you can see is, no one's laughing at my jokes. It's okay, it's morning right after spring break. But I do expect you to be better. This is where you say, maybe your jokes aren't good enough. And my answer to that is, I know, and I this is all you get. And what you can see is the analytical derivative and the numerical derivative correspond very nicely. So as we go through, we can estimate our numerical derivative at a bunch of different points. Just takes a computer to run each one of these. And they correspond really pretty well nearly everywhere. Okay, so if you don't know actually what the derivative is, you can just do this. Very nice. You probably all run into problems where this would be nice to do. Instead of writing down the functional form, you plot the relationship. Okay, any questions? So this is just a graph of the errors. So here I have, so remember back to the previous figure, I have the analytical and then I have the numerical. What I'm doing here is just plotting the errors. So let me actually just clear this. All I'm doing here is I'm taking the difference between the numerical derivative and the analytical derivative at each one of these values. And then I'm just plotting the difference between the two. That looks like this. Looks like this. So we have the difference between the analytical. So this is the numerical subtracted from minus the analytical. So if the value of these points is above 0, that means the difference between them leans in the direction of the numerical derivative. So the numerical derivative is greater than the analytical derivative when we're above, and then it's flipped. So the analytical derivative is greater when we're below 0. And what you can see here is there are systematic errors in the numerical derivative with respect to the analytical derivative. So for these small values, the analytical derivative is smaller. So we're overestimating the derivative using the numerical approach. And for these values, just slightly larger, the error goes in the other direction. We're slightly underestimating the derivative for those values. With very large values, we get pretty close. So this is actually very, very close. And if you look at the scale here, all of these are actually very close. But you can see there's a systematic mismatch between the two. And what we're going to do for the next couple of minutes here is actually fix this. This is using the one-sided derivative definition, where we're using this one-sided definition, right? So it's this thing. So we have f evaluated at an increment in one direction, subtracted, and then we're subtracting off the function evaluated at x. So this is what we call the one-sided derivative definition. And we're actually going to fix this systematic mismatch. We're going to make this better. It's not going to be perfect, but it's going to be less systematically wrong. We're going to do that right after we talk about higher order derivatives. And then I think that might be where we end for today. We end at 11:30, correct? Okay. So higher order derivatives, we can really do exactly the same thing, right? And the way you would maybe think about setting this up, if I hadn't been taught this, the way I would think about setting this problem up is I would just apply the derivative definition to the original derivative definition, right? Like the way you do this in math is you take the first derivative and then you take the first derivative of the first derivative. So it gives you the second derivative. And we can just really do the same thing in code. Applying the derivative definition to the derivative itself. So we take the dx, df prime of x with respect to dx, which is just this thing. So it's the limit definition, but using f prime instead. And then all we're going to do is just approximate this with some epsilon, which looks like this. So if you plug everything in, it looks like this. But let's write this in code. So this is the second derivative. So it's just the double prime. I'm using the subscript epsilon to tell us that we're using, this is not an instantaneous derivative. This is like the approximation using epsilon. So it looks like this. This is just the second derivative, so we're using exactly what we would like. So this is, f prime of the one side minus f prime at x, all over epsilon. If we plug everything in, we know what the derivative function using epsilon is. If we plug everything in, we get f of x plus 2 epsilon. We're just using the original definition of f prime using the epsilons, which ends up giving us 2 epsilon minus 2 times f of x plus epsilon. So if we go back just one step here, when I substitute this thing for our epsilon definition of f prime, we're plugging in x plus epsilon into our derivative definition for the function itself. So then we have those two it's like f of x plus 2 epsilon minus f of x plus the single epsilon. And then for this one, we need the increment of f. So we also have an f plus x plus epsilon. It's a lot to say, but that's how we end up with this too. And then the last thing we're left with is just the f of x. And the reason this is positive is because we're using, it's like a double negative. We're plugging in the derivative of the second bit, which gives us the negative from this second derivative definition, but then we also have the negative from the first derivative definition. So that's a lot to say, but that's where this thing is coming from. And then we're multiplying all of that by 1 over epsilon, so we have epsilon squared in the bottom. All right, any questions there? This is just the incremental version of the second derivative. And we can code this up just like we have for everything else. So, and what you can notice here is all we're using are the f's. You could plug the first derivative function into the first derivative function itself. But here we're just defining a second derivative using that whole math approach we just developed. Okay, so nice. So this is just the thing we wrote out in the previous slide, just coded up in Python. So the second derivative of this thing, you can probably see where this is going. Both of these things will drop out, and all we're left with is, so it's the double derivative of 2x squared. So it's 2 times 2 times 1. So it should be really, really close to 4. So the analytical derivative is 4, and the numerical derivative comes out to be very, very close. So we defined this thing just using the epsilon incremental approach. Here we plug in EZF, evaluated at 2 using our epsilon very close to 0, and that gives us something that we can go off of. So nice. This is the kind of thing I want you to be capable of thinking about these kinds of problems. We use math to help guide our thinking about solving these problems. We can really use Python to code lots and lots of things that we would do in math. as you work through your analytical problems, setting up like hiring decisions and firing decisions and all of that for your capstone, and like allocation of workers across different jobs and such, and you're setting up your problem, you can use code to help you think through these problems. I want you to have the skills to think through these problems, not just offload this to LLMs. LLMs will help you write the specific syntax for what you're doing, but being able to think about these things systematically can help you set up these analytical problems. Okay. Do you all have brain space for 8 more minutes? Can I talk you through one more thing? And then we'll be good to go. Like we showed earlier, there with the first derivative, we compared for the medium f, we have a mismatch between the analytical derivative and the numerical derivative. Right, I showed you that figure earlier. We had this thing. This is just, we have systematic error in one direction for these small values and for these medium values. Is there a way to fix this problem? And the answer is yes. So I'm going to show you, we use the simple derivative definition to give us the numerical derivative, but we can actually do slightly better. This has the best name in all of mathematics, the pt2 expansion. Okay, that was a pretty good one, I'd say.
What about pt2 series?
Yeah, pt2 series. My YouTube channel is actually called Taylor's Series. So you'll remember this. There's some beautiful mathematics behind where this comes from. If you're interested in this, 3 Blue 1 Brown on YouTube has a great visual explanation for where this comes from. But essentially, like the way we would write this, we're thinking about this the function evaluated at this value. We can write this as a series like this. I'm not going to get into the details here. What we call the Taylor expansion. And you can see some of the, so one detail I'll talk about is how this is evaluated. Just f of x, then we have f prime of x divided by the factorial of the derivative number. So this is divided by the factorial of 0, which is 1. This is divided by the factorial of 1, which is also 1, and so on. So this is second derivative divided by the factorial of 2. And then we have the increment raised to the second exponent, and so on. So this is just a series, goes out to infinity. We never will handle infinities with a computer. So why is this important? Well, when we're setting up our derivative definition, you can see a few things here. So we have f of x plus epsilon, and then we also have f of x on this side. So if we rearrange this, we can rewrite the Taylor series to look like this, which is exactly our derivative definition. When we have very small epsilon, we have, this is just the definition of f prime. So, thinking back to this thing, this is just f prime, and then we have a bunch of other stuff. And when the increment epsilon is very, very small, so you can see here we have epsilon. When this is very small, these extra derivative terms are also going to be very small. So the error, this thing, this is the derivative definition for increments, like not at epsilon going to 0, but at meaningful increments, even though they're very small. All of these terms are going to be incredibly close to 0. And they're going to get closer and closer to 0 every time we raise them to a larger increment. A larger exponent. So these are all going to be pretty close to 0. So we're going to call them big O of E. So this is just like big O notation if you've seen it. So this thing is just, it's not 0, but it's very close to 0. And if we were to rearrange this, we can like apply the same kind of reasoning to the second derivatives and write this all out in terms of a Taylor expansion. So where in the slides do we, so we can write all of this out with our actual numbers. So this is all with, you know, the second derivative and such. There's a lot of math here. I don't want to get into all of the math. The main idea for why we think about all of this is to try to improve our numerical derivative solution. Before we were using one side. So we were looking at an epsilon moving in one direction, but then evaluating the other side at x. But what if we use the Taylor series to set up a two-sided epsilon? So instead of evaluating at x and then x plus epsilon or x minus epsilon, either direction, what if we look at x plus epsilon and x minus epsilon? And as you can see with the Taylor series, for both of these directions, you can see all of the larger terms are actually sort of going to cancel out. So we have this thing and this thing. We have f of x. We have f of x minus, f prime of x times epsilon, and so on. A lot of these terms cancel, which is really, really nice. When we rearrange this, we get this thing. So this is the definition of a centered difference equation, which is equal. So we're just taking the difference here, essentially combining these the two sides to get f prime. Our error term, our big O, is of the epsilon squared. So the mismatch between the derivative, the analytical derivative using some non-zero epsilon, and the true mathematical definition of this expansion, our big O, is of epsilon squared. So what this is telling us is that the error, the mismatch between the numerical and the analytical, is smaller when we use the two-sided approach instead of the one-sided approach. So there are lots of details for how we derive this thing. We're running up against the end of class time. But this is essentially the main idea, is a two-sided approach can actually do better for us. So I'm going to run this and then show you a picture of this. So here I have the forward difference, which is our main the first analytical, numerical derivative that we defined. But then using the two-sided approach, the centered difference approach in yellow, you can see the mismatch, the error is much, much smaller. It's on the order of epsilon times the original error. So we've essentially used the Taylor series to fix some of the underlying mismatch that we saw earlier. Okay, and there are ways of taking this even further to set up error terms that are on the order of like higher order epsilons. But in general, this is going to be more than fine. And in the built-in packages are going to give you really nice solutions like this. Okay, so this is a lot, I think, right up at the end of class. Stick around if you have questions. Nice meeting all of you. I will forget some of your names, I'm sure, in which case you'll have to give me lecture points. I'll see you all on Thursday. Let's see. Yeah, see you on Thursday. Stick around if you have questions.